Hello and welcome to this video on the dangers of radioactivity, which is part of the nuclear physics topic in AQA A-Level Physics. So in today's lesson we're going to try and understand the impact of radiation on humans. So if we've been successful and learned in today's lesson, we should be able to identify the different units of radiation, look at how we can measure the effect of radiation in humans, and finally write a risk assessment for handling radioactive materials. Now this forms part of the AQA specification in 3.8.1.2, alpha, beta and gamma radiation, in particular looking at the applications and the background radiation. So the first unit of radioactivity we've got to consider is the becquerel. Now 1 becquerel is defined as the activity of a quantity of radioactive material in which 1 nucleus decays per second. So therefore the becquerel unit is equivalent to an inverse second. So 1 becquerel is 1 second to the minus 1. So the becquerel, which is the unit of pretty much disintegration, is named after Henri Becquerel, who shared a Nobel Prize with Pierre and Marie Curie in 1903 for their work in discovering radioactivity. Now it's important that at A-level physics we only assume that when a nucleus decays it will produce 1 radioactive particle. So this means the activity can also be defined as the number of radioactive particles produced every second by a sample. Now the next unit of radiation is the Gray. Now this is the SI derived unit of absorbed dose of radiation. So we define a Gray as the absorption of 1 joule of such energy by 1 kilogram of matter. Now the Gray was named after the British physicist Lewis Gray, who was a pioneer in the field of the measurement of radium radiation and X-rays and their effects on living tissue. So fundamentally the Gray measures how much energy is deposited into a mass via ionizing radiation. Now the final unit of radiation which we've got to be aware of is the Sievert, which is the SI unit of effective radiation dose. So Sieverts represent the biological effects of ionizing radiation. So when you've got to consider the biological effects of radiation, further calculations have to be performed to convert the absorbed dose of energy, which is given by the Gray, into an effective dose, which depends on the type of radiation and the biological context of where that radiation hits. Now the Sievert is named after Rolf Sievert, who was a Swedish medical physicist renowned for his work on radiation dosage measurement and research into the biological effects of radiation. So you've got to be aware that the Sievert differs from the Gray due to the type of tissue the ionizing radiation hits and the ionizing power of that radiation. So the Gray and the Sievert units are both based on the measurement of the concentration of ionizing radiation absorbed per unit of a material's mass. So therefore this means that the Gray and the Sievert will share the same SI unit. However, despite this commonality, the Sievert and the Gray are only interchangeable for certain kinds of radiation. Now we state that the Sievert has the units of joules per kilogram equivalent because the equivalent incorporates the features of human tissue and the type of radiation which haven't been mentioned prior to this. So we say that the Gray is used to express the physical quantity of the absorbed dose, which is the amount of energy absorbed per unit mass in any material, whilst the Sievert is used to express the biological equivalent dose to human tissue. So as the Sievert has a biological effects component to it, a corrective factor, which we call the weighting factor or radiation quality, is applied to convert the physical unit of the Gray into the biological effects unit that is the Sievert. So we've got our absorbed dose, which is the Gray, but when we incorporate our radiation weighting factor, which links into the type of radiation used, and we link it into the tissue weighting factor, the factor caused by where that radiation hits, it will turn your Gray into the Sievert. So the weighting factor depends on the type of radiation, type of tissue irradiated and the type of radiation used. So we can link the units as follows. So the becquerels shows the activity of radiation, or how many decays there are per second. The Grays act as a measure of how much energy the radiation is deposited per kilogram, whilst the Sievert indicates the damage that radiation can lead into the typical human body. And you can convert between Grays and Sieverts with weighting factors due to the radiation type, where we know the greater the ionizing ability, the greater weighting factor, and the tissue with which the radiation hits. So here we can see in the following diagram the link shown between your becquerels, your Grays and your Sieverts. Now, previously we have looked at the inverse square law, and we've looked at cobalt as a gamma emitter. Now we can say that the number of radioactive decays it carries out per second is on the order of about 10 to the 5, so this indicates the activity of the radioactive source is about 10 to the 5 becquerels. Now we know that each radioactive particle emitted by cobalt has an energy of about 10 to the minus 13 joules, so therefore it indicates to us that every second the source emits about 10 to the minus 8 joules, because we've got each particle with an energy of about 10 to the minus 13 joules and 10 to the 5 particles emitted every second. So this tells us that in a typical experiment you carry out in school, the source will emit about 10 to the minus 5 joules. Now it's important to note that if we assume that the entire energy is absorbed by a human of order of about 10 to the 2 kilograms, about 80 kilograms, okay, that's a sensible suggestion, if not an overestimation, then the radiation dose you would receive is about 10 to the minus 7 joules per kilogram, because it would be 10 to the minus 5 divided by 10 to the 2. So in that particular experiment you will receive in maximum about 10 to the minus 7 grays. Now if we assume that the part of the body which absorbs the radiation is the skin, and the radiation is solely gamma radiation, that considers for our weighting factor, we get about 10 to the minus 6 sieverts. Now this is not harmful, but it's not insignificant, so precautions need to be taken, and remember any exposure needs to be considered as a possible risk to ionization, because radiation is stochastic. There's no lower safe limit for the amount of radiation you can absorb. Now since ionizing radiation is stochastic, we've got to always consider the biological effects of any radiation, and this includes the biological effects of the background radiation found all around us. Now here you can see some of the measurements of the sieverts you receive each year from just living on the planet Earth. So as you can see, every human does receive a sizable body dose of radiation each year, which is just the background radiation found on the Earth. Now generally, to help you understand this diagram well, one sievert gives you a 5.5% chance of developing cancer. Now you can see by the values that we've got microsieverts and millisieverts that the background radiation is very unlikely to cause you to develop cancer. However, because radiation is stochastic, it is still possible because there's no lower safe limit. So there are many different sources of background radiation, and these include firstly the air, because radioactive radon gas is released from rocks and it emits alpha radiation. The concentration of this gas in the atmosphere varies from place to place, and it's usually the largest contributor to the background radiation. It also includes ground and buildings, because nearly all rocks contain radioactive isotopes. It includes cosmic radiation, because cosmic ray particles, mainly high energy protons from space, can lead to radiation being produced, because they will collide with particles in the upper atmosphere of the Earth, producing this nuclear radiation. Another source of background radiation is living organisms, because all plants and animals contain carbon, and some of this will actually be the radioactive carbon-14 isotope. And finally, we've got artificial radiation from medical and industrial sources, which will make up a small amount of the background radiation. So on Earth you are surrounded by particles giving off radiation. Indeed, most substances and objects are radioactive. They do emit ionizing radiation. Now humans give off ionizing radiation themselves, typically about 7,000 becquerels. However, most of the resultant ionizing radiation is absorbed within the owner's own body, so actually the human doesn't actually release as much ionizing radiation as 7,000 becquerels. So we've got to consider a few things with these ideas. Do we define every substance which gives off radiation as radioactive? Do we have to treat all substances which give off radiation with the same safety procedures, and are humans actually classed as radioactive? So, what do we define as radioactive, and what criteria do we place on an object to make it radioactive? So the Radiation Protection Division of the Health Protection Agency defines a radioactive substance as having an activity of 400 becquerels per kilogram. So for the typical mass of a human being about 70 kilograms, we can say that it has to have an activity of about 100 becquerels per kilogram. So therefore, it's not actually radioactive, but because we're below this lower threshold, because whilst the threshold for being radioactive is 400 becquerels per kilogram, a human has an activity of 100 becquerels per kilogram. So humans do not need to be treated with radioactivity safety measures. Now, when we're considering background radiation, you've got to remember that when you take a reading of the count rate from a radioactive source, you must measure the background radiation count separately and then subtract it from your measurement. Now, to do this accurately, you've got to take at least 3 readings of the count rate using a Geiger counter without a radioactive source present. You then average these readings and subtract this average from each measurement you take of a radioactive source's count rate. So you would have the total count rate, which is just everything with the radioactive source and the room it is in. You can then work out your corrected count rate by subtracting the background radiation from that. So since it's believed that there's no limit below which ionizing radiation is harmless due to the stochastic nature of radioactivity, it's recommended that exposure to ionizing radiation should be as low as reasonably practical or achievable. Now, we abbreviate this to ALARA, as low as reasonably achievable, and we need to consider how to achieve ALARA status when using radiation. So you've got to always remember that there is some risk with using radiation. Now, never state in an examination that you've removed a risk, you've only ever reduced the risk. Now, evidence for this fact that there's no low safe limit comes from studies of long-term health of survivors of nuclear disasters such as Chernobyl. So let's look at some guidelines. Firstly, radioactive materials must be stored and used with care to prevent contamination or radiation poisoning, a form of radiation. So you must be aware of the guidelines in place from the government to safely store and use radioactive materials. Again, materials with an activity greater than 400 becquerels per kilogram. So the first rule is the storage of radioactive materials in a lead-lined container. Now, most radioactive sources will produce gamma radiation as well as alpha or beta. Now, the lead lining of the container must be thick enough to reduce the gamma radiation from the sources in the container so it goes to the level of the background radiation. The second rule is that regulations require that containers are under lock and key and the storage facilities are checked to see if they are effective in reducing radiation. So it tends to be that many sources are kept in a lock room in an office. Now, in schools, there's someone called an RPS, a radiation protection officer, who is in charge of checking the radioactive sources, which is done once a year, and they're going to fill in a form regarding this, which is sent off to the National Standards Agency. Rule 3 is that no source should ever come into contact with your skin. So solid sources should be transferred using tools like tongs, like a glove box, like a robot. So this ensures that the distance between the source and the experimenter is practical, yet the intensity of gamma radiation is low and the user is beyond the range of alpha and beta. The fourth rule is that radioactive liquids, gases and powders are held in sealed containers. Now, this ensures that the gas can't be breathed in and the radioactive liquid or powder cannot be ingested. Then, in rule 5 is that radioactive sources should not be used for longer than necessary, because the longer a person is exposed to ionizing radiation, the greater the dose of radiation received. Now, if the 5 rules, the 3 rules including the using and 2 the storing are followed, then ALARA will be achieved. So if we have learnt in today's lesson, we should be able to understand the applications of handling radioactive sources, understand background radiation, examples of its origins, and experimental elimination from calculations. So if we've been successful and learnt in today's lesson, we should be able to identify the different units of radiation, look at how we can measure the effect of radiation in humans, and then finally write a risk assessment for handling radioactive materials. So I hope you've enjoyed today's lesson on the dangers of radioactivity, which is part of the nuclear physics topic in AQA A-Level Physics. Thank you very much and have a lovely day.